Hello, everyone. My name is Sina Kalantarzadeh. I am a fourth-year bachelor student at University of Technology in Iran. Uh, I am very happy to be here, and uh, today we are gonna to talk about a parameter in graphs denoted as inverse degree, and we try to characterize the graphs which this parameter is maximized for them. We have done this work with my friend Kasra and under supervision of Dr. Akbari and Dr. Nematullah. So first we have a definition about a inverse degree of G, which as you see, inverse degree of G is denoted as sum of inverse degrees of all vertices of G. As you see, these are two examples which we calculate the inverse degree of them, and emphasize that we don't need to be to the graph to be connected for defining inverse degree. We have another definition. Let G be a connected graph of order n and size m. We call G an nm maxide graph. If inverse degree of it is maximum among all connected graphs of order n and size m. We are going to see some examples again. If the number of edges is equal to number of vertices minus 1, I mean, if we want to talk about the trees, we can conclude that we can see that Sn, I mean the star, is the only maxide graph among all trees. And we are the second example. As you see, it has 8 vertices and 15 edges, which is unique among all the 15 maxide graphs. Here are more examples. As you see, if you look more closely, you can see that these graphs have a special structure, and they may have some common features. The first common feature we are gonna to prove for these graphs is that all of these graphs have a vertex that is connected to all other vertices. So we state this as our first lemma. Let G be an n maxide graph, then delta of G is equal to n minus 1. And we are gonna to prove it. We assume by contradiction that the statement doesn't hold. So we consider the vertex U, which its degree is equal to delta of G, and we assume that it is less than n minus 1. Here is U, and these are the neighbors of U, and these are all other vertices. Since G is connected, we can see that there must be an edge which comes out of NU, and assume that vertices V and W are incident to it. Here you see a violet line, which when I use this in a slide, I mean there is no edge there. So we delete edge E and add the other edge F to obtain the new graph H, which you can see that it remains connected. Why? Because any path that uses E before, it can use F and edge UV instead. And also by some calculations, we can see that ID of H is strictly greater than ID of G, which is a contradiction. So now we have proved that delta of max ID graphs is always equal to n minus 1. Again, we see uh, our examples, and we are going to we try to prove another feature for them. As you can see, in each of these graphs, the vertex of lowest degree has the property that all its neighbors have degree n minus 1. You can see here that this is a leaf, and its neighbor have degree n minus 1. And we are going to prove this as our as a lemma 2. So consider a graph G, which is max ID graph, and consider a vertex such that degree of it is equal to delta of G. And we state that any neighbors of V have degree n minus 1. Again, for prove it by contradiction, we assume that this doesn't hold. So we consider one of its neighbors, which has the degree less than n minus 1. As you see, this is V, and this is U, and all of these are neighbors of U. And by our assumption, we can see that there exists a vertex W out of NAU. Again, we delete E and add edge F to obtain the new graph H, which again, we can see that it is connected Y. We can apply our previous lemma, which states that there exists the vertex of degree n minus 1 in G, and it is unchanged in H, so we can see that H is connected. And again, we can see that by calculations that ID of H is greater than ID of G. So we round to a contradiction again. So far now, we have proved these two properties for max ID graphs. You might think with yourself that we have proved a property about of degree of neighbors of lowest degree, but what about its degree itself? As you see, we can't say anything general about the lowest degree of a graph. You see in this graph, the delta of G is equal to 3. But in most of the graphs, we can see that delta of G is equal to 1. So why is that? If you look more closely, you can see that we can't change a degree of any vertices in this graph to 1 by our method. I mean, deleting an edge and adding another one to it. It is because that it has a lot of edges. It has many edges, and we can do it. As you see, this graph have a special structure, and we are going to talk about it in our first survey. Okay, let's G be a max ID graph, which this inequality holds for its number of edges and a number of vertices. I mean, number of edges is very high. Also, suppose that Vx to Vn are vertices of G, and we have sorted them respect to their degrees. This theorem states that all vertices except V1 forms a Kn minus 1. You can see that shape of G is as follows. To prove it, we have two following cases. If delta of G is equal to 1, it is easy to see that the structure and the shape of G is as you see in here, and the hard case is case 2. So in this case, we assume that the delta of G is greater than 1, and we are going to discuss more about it. Let K equals to degree of V1 and assume that the neighbors of V1 are these vertices, which we can see that degree of all of them is equal to n minus 1 according to our lemma 2. Again, by contradiction, we assume that the induced graph on vertices V2 to Vn is not complete, and we let S be the number of edges which must have to be added to G1 to turn into a complete graph. I mean, S is the number of these violet lines. By our assumption, and we label these edges as E1 to EK, and as before, we delete all edges E1 to ES from G and add them to graph G1 to make it a complete graph, which you can see that H turns into this graph, and again we can see that H remains connected with this change, and also the same scenario, ID of H is greater than ID of G. And again, we run into a contradiction. So we have
sorry for interruption. You have 4 minutes left. We have 5 minutes for questions. Just maybe you can skip some
all right.
details.
All right.
Sorry.
Okay. So we have proved that we have see that the shape of graphs which have many edges and then we want to talk about the shape of these graphs which don't have many edges. We can prove that delta of I mean the lowest degree of them is equal to 1. We skip the proof, and for our purpose to determine the shape of these graphs, we need this lemma, which yells that if G is a max ID graph and has the lowest degree equal to 1, and if V be the vertex of degree 1, if we delete V from G, we obtain another max ID graph, and we again skip the proof of it. So right now we have all tools to determine the shape of the graphs which their number of edges is less than n-1 choose 2. We assume that T be the largest positive integer such that T choose 2 is less than or equal m minus n plus 1. Then we said that G has the following properties. The first property is that G has at least n minus t minus 2 vertices of degree 1. And the second one is that the t plus 1 vertices of the highest degree in G forms a k t plus 1. Uh, uh, this is the schema of these two properties. And again, I think I can, how many minutes I have? How much minutes I have?
2 or 3
I think
minutes.
about 1 or 2 minutes. Uh, all right. So I want to talk about proof of this a little bit. Uh, uh, Before to prove that, we have some observation, which the first one is that a delta of G is equal to 1. And we assume that G have L vertices of degree 1, which denoted as V1 to VL. And also we know from lemma 1 that G has a vertex of degree n minus 1 called U. And now we construct this graph G0 to GL as follows. We let G0 equal to G itself. And for I greater than 1, we delete vertex Vi from Gi minus 1 to obtain Gi. So after doing this L times, we obtain the graph GL, which you can see that it doesn't have any vertices of degree 1. And also from our previous lemma, we can see that all these graphs in this sequence are max-ID graphs, so as GL. So our first property, if the number of vertices of degree 1 is less than n minus t minus 2, we can see that delta of GL is greater than 2. And since it is a max ID graph, we have this inequality for between its number of edges and number of vertices from our theorem 1, which by some conclusions we can we ran into a contradiction. And for the second property, we let K equals to n minus t minus 2, and we consider one of the that graphs, I mean GK, which you can see GK is obtained of G after deleting vertices Vx to Vk. And you can see that GK has t plus 2 vertices, and it is also a max ID graph. And this inequality holds for its number of edges and a number of its vertices. And as we proved in theorem 1, we can see that t plus 1 vertices of largest degree in GK forms a complete graph of order t plus 1, which they form a complete graph in a G2. So after all theorems and lemmas, we have this corollary, which states that if G is a max ID graph and VH, we want to Vn beats all vertices, which we have sorted them respect to their degrees, and also assuming that t be the largest positive integer such that this inequality holds for it. We can see that the shape of G is unique, I mean without considering the isomorphism, and the shape is as follows. As you can see, these are t minus 2 vertices of degree 1. This Vx is the vertex that has degree n minus 1, and these all vertices forms a complete graph of order t plus 1, and the last vertex I mean vt plus 2 is adjacent to some of these graphs. And as you can see, this shape is unique. And also we can obtain that the degree sequence of G is as follows. And I'm finished. Thank you for your attention. And again, I'm sorry about my lateness. It wasn't my fault, but I should predict that. I should have predicted.
That's fine. Thank you for your good talk. Are there any quick questions? Because we are running out of time, unfortunately. If you have any questions, you can ask Sina after. So thanks, Sina, by reacting emojis.